Hello everyone, welcome to the last video on exercises for this class. Today we're going to be studying a Fourier series calculation of a periodic signal. In this case it's a triangular signal, and the problem is specifically asking to use a Fourier series based on cosine and sine terms. Essentially what the homework 7 is asking with the an and bn terms. There's another complex series definition which is equivalent to this one, but it's based on a cn term which is complex and is related to an and bn, but you need to do some extra work. Those are two approaches to get the FFT. One thing that I wanted to go before solving anything, and it's a good tip overall whenever you're solving this type of problems, it's that you can identify for these periodic signals some type of symmetry. That it's gonna highly simplify your calculations. So I pasted here the same table that is provided on the book, which is all types of symmetry that are present on periodic signals, which are even, odd, half wave, and a combination, half wave and even, and half wave and odd. So we need to identify in this case what is the symmetry present on a signal. By the way, it's important to mention also that some signals do not have any type of symmetry, and you need to go ahead and get all the indexes, AN, BN, and A0. But in most cases, I would say, they do have symmetry, and we can definitely simplify the calculations. So first of all, can we say that the function is even or odd? Well, easily we can get that the function is odd because it satisfies this condition, meaning that if we get some f of t, let's say this one, and we get this same point, which is at 1.5, right? Now for negative time, right? So negative 1.5 seconds, it's going to be here. And we get the same value for negative, right? But so what's the conclusion of this? That f of t, which is this value, equals minus f of minus t. So minus this value is going to be exactly the same. So our function has odd symmetry. Right? And let's see if it has halfway symmetry. And how do we get that? Applying one of these definitions, right? So if we have one f of t, and then we move half a cycle, in this case one cycle is exactly 2 seconds. So let's say we're here at the same point, and we move half a cycle. That means we move 1 second. So we're on 1.5, we're going to be on 0.5. What is going to be the value of the signal? Minus f of t minus t half. So that means that fulfills this condition, right? Because of this minus sign here. You can try this with a plus sign, and you're going to move this way, right? And you're going to get this value. Same conclusion. So in this case, we have two conditions met. One is odd, and the other is halfway. So half wave, sorry. So we do have a lot of simplifications. That's the idea with this whole exercise, that we can definitely simplify our calculations. So in our case is half wave and odd. So this is what we have. Sorry, I wanted to highlight this one. Halfway and odd. That means that this is what we're gonna use, right? An equals 0 because the function is odd, so definitely an equals 0, and bn equals this. So instead of integrating the whole period or half of the period, we're just integrating 1/4 of the period, because that's enough to capture all the spectral information of that function. So let's keep going, and now we can use the simplifications to calculate solution. So we have here that, let's say, the function has half weight and odd symmetry. Therefore an equals 0. No need to calculate that one. And then bn equals we'll have to 8 over t integral 0 from t4 FFT sine of n omega naught t dt for n odd and 0 for n even. Those are the two conditions that simplify our calculations for this function. So the other important thing is we don't need to define the function for the whole period t. We just need to define it for the integration period, which in this case is t over 4. So we can say the function is defined as f of t equals minus 4t for that period, 0 to t over 4, right? Which is essentially this. That's 1/4 of the period, and that's going to be the function. If we don't use that symmetry, then we need to define this function as a piecewise linear function, essentially. That would be one, this would be another piece, and this would be another piece. So we need to define 3 linear segments that we're going to be integrating, and that's going to make everything way more complicated. You're going to get to the same result, but definitely it's going to take way, way longer. So that's going to be the definition of the function. And also we can say that the period, in this case, it's 2 seconds, and omega naught, it's going to be 2 pi divided by t, which is essentially t equals 2, so 2 over 2, get rid of that, and pi radians per second. So omega naught, it's pi, essentially. So with that information, we can go ahead and start to calculate this bn. So by definition, bn is going to be, sorry, I forgot that, t over 4, the function f of t sine of n omega naught t dt. Okay, so now we can, t is 2, right? T is 2, so 8 divided by 2 is going to give us 4 here. And then we have 0. T is 2 again, then 2 divided by 4, that's 1/2. And then we have the function that is minus 4t, already defined, times sine of n omega naught, which is pi t dt. So now we need to calculate this integral. Everyone should be at this point very familiar on how to calculate this. So I'm going to go ahead and just write down the solution for this integral. You can do it on your side, but I think this is very familiar for everyone. 4 times 4 is minus 16. I put that outside, and the integral should give you pi square n square sine of n pi t minus n pi t over n square pi square cosine of n pi t. Okay, and this is between 0 and 1 over 2. Simple. Check it on your side, make sure that you get this step. Once we have that, we can reorganize everything, get rid of the additional terms, and we're gonna get here, let's put cosine. So the minus sign, let's move it inside to make it simpler here. 16, so the term with the cosine, the n pi is gonna get rid of this too. So we're gonna have t over n pi cosine of n pi t, and then we have the minus sign for this guy here, 1 over n square pi square sine of n pi t, from 0 to 1 over 2. And now we can evaluate this function, right? Now we can evaluate this function. This is going to be 16 over whatever this function is evaluated at t equals 1 over 2. So that is going to be, let's make the first term, 1 over 2 n pi cosine of n pi over 2 minus 1 over n squared pi square sine of n pi over 2. Again, we're replacing t equals 1 over 2 here, minus this same function evaluated at t equals 0. So this is going to give us cosine of 0, which is going to be 1, minus sine of 0, essentially, which is 0 in this case, right? Actually, this one is 0 because of the, right? We're evaluating at t equals 0, so we put 0 here, 0 here. The cosine, it's going to be 1, but we have the 0 on top, so 0 here. Sine of 0, this is going to be 0. Okay, so we keep going here, and we get essentially 16. Now we can simplify this whole thing. 1 over 2 n pi cosine of n pi over 2. So you can see that n is going to be an integer that goes from 1 to basically infinity. So we're going to have pi over 2, then 2 pi over 2, then 3 pi over 2. All those values are going to give us 0, right? Because n is odd, right? We define that here. N is odd. So that means n is going to be 1, 3, 5, and so on. What does it mean? That we're evaluating cosine of pi over 2, 0, cosine of 3 pi over 2, 0, cosine of 5 pi over 2, 0. So we can use that definition to get rid of that. So essentially, we're going to say this is 0. It's red for this, 0, because n is odd. And then we have the sine portion that definitely is going to be different than 0. We said n square pi square sine of n pi over 2. Okay, so that means that we simplify this part and we get negative 16 over n square pi square sine of n pi over 2. And that's pretty much it, right? If you leave it at this point, that's going to be correct. However, for the math interested people, you know that for n odd, right, Don't forget that n is odd. So if we evaluate n equals 1, it's going to give us the sign of that pi over 2 is going to give us essentially 1, right? For n equals 3, then we're going to evaluate sine of 3 pi over 2. That is going to give us minus 1. For n equals 5, then we're going to have 1. For n equals 7, they're going to have minus 1. And you see this pattern here? So we can change, actually, we can rewrite this sine of n pi over 2 using powers of minus 1. So again, this is completely optional. If your solution is up to here, that's completely fine. So this is the equivalent way to write it down in terms of powers of minus 1. You can write it like that, or you can write it like this, which is going to be minus 1 over n minus 1 plus 1 over 2. This is actually plus 1. And that would be the Bn component. One more time, this is the solution. That's completely fine. You can go one step further and simplify it. It's just a math thing. So f of t ultimately is going to be the summation from n equals 1 to infinity, but using odd numbers, right? So it's going to be 1, 3, 5, and so on, up to infinity. Whoop. There we go, up to infinity of Bn, which is the essentially our, actually not, I was correct with this one. So this is minus 2, and we absorbed that negative sign to make it plus 1. Okay, that's correct. So it's going to be n plus 1 over 2 times 16 over n squared pi square times the sine, right? Sine of n omega naught, which in this case is pi t. That's the function represented as a sum of essentially its phasors, right? You can see that this thing is going to be the module, and this is going to be the frequency. The angle in this case is 0 every time. That's the module of that signal. When n equals 1, then you're going to have a phasor, essentially, right? The module r and an angle that in this case is 0. For n equals 3, then you're going to have another module that is going to be some r3, let's call this r1, angle 0, and so on. So you're going to have essentially phasors that are going to represent this function for all the harmonics, including the fundamental. And as we go up with n, right, the smallest the magnitude, because n is in the denominator here. So the harmonics for this function are decreasing as long as we go up with the n count. So the more elements that we add, it's less information every time that we're adding to the signal. So that's a clear indication that at some point we're going to add some information that is going to be somewhat irrelevant. And that's actually one of the virtues of the FFT, that we can at some point truncate the function, and instead of doing the infinite sum, then we're going to use, let's say, 100 terms, or we're going to use 10 terms, or we're going to use 5 terms. Whatever is enough that this function is going to be represented. In engineering, we call it good enough, right? So that's the main result here. An in this case is 0. So let me go back to the beginning here. A naught is 0 because of the odd symmetry. AN is 0 because of the odd symmetry. And Bn is defined only for odd numbers of n because of the halfway symmetry. So this is 0, this is 0, and we get only this portion. So that's pretty much this problem, and what we're going to do on the next video, it's verifying this solution using MATLAB. So see you on the other side.